In this video, I'll be building a leg module for a quadruped robot, which is the most complex part and has a major impact on overall performance. I'll walk you through the entire process from design and machining to assembly and motion testing. For the first time, I'll also be machining aluminum using a desktop CNC machine. Let's follow the development process together, including all the trial and error along the way. In many quadruped robots, the motor that drives the knee is actually not placed at the knee itself, but closer to the shoulder. Mounting an actuator directly at the knee would be mechanically simpler, but it would also increase the moment of inertia of the leg. The moment of inertia is a measure of how hard it is to rotate an object. The farther the mass is from the axis of rotation, the harder it is to move. For example, think about a stick with a weight attached to one end. If you hold the stick by the opposite end and try to swing it, it feels heavy. But if you hold it near the weight and rotate it, it feels much lighter. Now apply this idea to a robot leg. If you put a heavy motor around the knee or the foot, the leg will have a large moment of inertia when you try to swing it forward and backward, which makes fast motion difficult. On the other hand, if you move the motor closer to the shoulder, the inertia seen at the foot becomes smaller and the leg can move more quickly and responsively. If we flip the viewpoint and treat the foot in contact with the ground as the rotation center, placing the motor closer to the shoulder increases the moment of inertia around that point. This gives the robot a bit more time before it tips over, which effectively improves its stability. So by placing the knee motor near the shoulder, we can achieve both higher agility and better stability for the quadruped robot. However, if you place the motor at the shoulder, you need some kind of transmission to carry the rotation down to the knee. Common options for driving the knee are timing belts, linkage mechanisms, and ball screws. In this project, I chose to use a ball screw. They all have their own functional pros and cons, but my main reason here was actually very simple. With this structure, I can make the robot look the most beautiful. By using a ball screw, I can mount the motor vertically, which lets me design the entire leg as a clean, cylindrical shape. I really like this kind of streamlined, flowing design, and that preference is what ultimately shaped the knee mechanism in this project. Here is the actual design I ended up with. The motor rotates the ball screw and pushes the nut forward in a straight line. That linear motion drives the linkage, and as a result, the knee joint rotates. I've embedded magnets in the knee joint and use a magnetic encoder to measure the angle precisely. The range of motion is wide enough, and there's no mechanical interference anywhere in the stroke. I'm also really happy with the design. Because I can mount the motor vertically, I was able to shape the entire leg into a smooth, streamlined form. For the color scheme, the outer surfaces are black and the inner structure is white. Black gives a tighter, more slim look, so this combination makes the leg appear thinner than it actually is. Most of the visible structure is intended to be 3D printed plastic parts, which makes prototyping cheap and easy. On the other hand, the area around the actuator generates a lot of heat, so for long-time operation, heat dissipation is critical. That's why this part really has to be made from aluminum. However, outsourcing aluminum CNC machining is quite expensive, and it's hard to iterate prototypes over and over like you can with 3D printing. In the worst case, the parts might arrive and you discover something fundamental is off. For example, the bearings don't even fit. To solve all of these problems, I'm using the sponsor of this video, Makera Desktop CNC Carvera Air. With this machine, I can mill aluminum parts at home without outsourcing and remake them as many times as I want while fine-tuning the dimensions. But honestly, doing CNC machining at home sounds pretty intimidating, right? In fact, this is my very first time ever using a CNC machine. I'm a complete beginner. So in this video, I'd like you to follow my journey from zero experience to successfully cutting aluminum parts. And through that process, I hope you can really feel how easy Carvera Air is to use. Carvera Air comes with built-in tutorials, so I'll start by learning from those first. To run a job on Carvera Air, you only need 4 things. First, the material block. You clamp the aluminum or plastic block you want to cut like this. Next, the bit. This rotating tool is what actually cuts the material. Then the NC file, a file that records all the machining steps and tool paths. And finally, the controller app. You connect to Carvera Air from your PC and execute the NC file directly. Normally, you would have to create the NC file yourself, but in the tutorial, the NC file is already included in the controller app, so all you have to do is press the start button. When you start the job, the machine first asks you to attach the probe. Once you mount the probe, it automatically performs calibration and accurately detects the work area. Thanks to that, it can prevent accidents like crashing into the clamps. After calibration, instructions for changing the bit are displayed on screen. In this way, every operation you need during machining is guided by the app, so you just follow the steps on the screen and can machine safely. It's really very simple. The tutorial is completed just by going through this flow. In this project, I'm only using 3-axis machining to cut metal parts, but with optional modules, Carvera Air also supports laser engraving and 4-axis machining. I genuinely feel this is a machine that can revolutionize DIY. For more details about the Carvera Air, please check the video description. From here, we're going to actually machine the 3 aluminum parts that form the heart of this leg module. We'll start with this part. We'll machine the main part out of the round aluminum block on the left and use the square block on the right as a jig for centering during the double-sided machining. First, we make the jig. We machine the mounting holes so the jig can be bolted directly onto the Carvera Air. Then we machine a hole for the round block to sit in. This way, even if we flip it over, the position of the center doesn't shift. We also drill holes for the screws and tap matching screw holes in the round block so we can fasten it firmly to the jig. Once everything is set up, we start by machining the top side. It came out very clean, exactly as designed. Next, we flip it, fix it back onto the jig, and machine the back side. The back side is now complete. It looks extremely clean. Next, we cut the part free from the stock. Finally, we cut the tabs with a small saw and clean up the edges to finish the part. That completes the first part. The finish is really beautiful, and it's honestly amazing that you can do this kind of machining at home. Next, we machine the second part out of this block. The process is the same. We machine the front side, fix it to the jig to machine the back side, then cut it free and clean up the edges. That finishes the second part as well. Finally, we machine the third part. The steps are the same. We machine the top, mount it on the jig to machine the back, then cut it off and tidy it up. With that, all 3 aluminum parts are fully machined. Next, we move on to machining steel parts instead of aluminum. This time, we're working with a commercially available ball screw. To fit it into my design, I'll shorten the shaft and machine a groove so it can be connected to the actuator. First, I adjust the length of the ball screw using a cut-off saw. Looks good. Next, I machine the groove for the actuator connection using the Carvera Air. I made a dedicated jig for this step, and the ball screw is fixed securely in the jig before machining. Metal machining on the Carvera Air is mainly intended for relatively soft materials like aluminum and brass, but harder materials such as steel can also be machined occasionally, as long as the cutting depth is shallow and the feed rate is slow. This makes it a good fit for situations like this, where you want to make small adjustments to off-the-shelf steel parts to match your own design. As you can see, the groove was machined cleanly and the ball screw fits perfectly into the actuator. With the metal parts finished, we can now move on to assembling the actuator. First, let's start by building the rotor. Using this red jig, I glue 2 10mm magnets together to make a single 20mm magnet. For the yoke, I use a mild steel ring. Because mild steel is ferromagnetic, it helps confine the magnetic flux efficiently, which leads to higher actuator torque. Next, I assemble all of the parts using adhesive. The magnets are arranged so that their polarities alternate. To measure the rotor's rotational angle with a magnetic encoder, I also embed a radially magnetized magnet into the shaft. Finally, I clean up the excess adhesive by polishing it off. With that, the rotor is complete. Next, I assemble the remaining components. First, I press fit the bearings. This is one of the most critical parts of the entire actuator. As you can see, the bearing fits perfectly, with no gaps at all. This really shows the machining accuracy of the Carvera Air. After that, I just need to install the stator, the cooling fan, the thermal pad, and the FOC control driver to complete the assembly. However, a problem came up at this point. While repeatedly removing and reinstalling the bearings behind the scenes during filming, I ended up damaging the rotor shaft. As a result, the rotor developed play and started to tilt like this. Because of that, the rotor began to contact other components and could no longer rotate properly. So I had to fix it. I machined away the damaged shaft, made a new shaft, and replaced it. The fix is now complete. As you can see, the rotor spins smoothly with no contact, and with that, the actuator is finished. Next, I'll move on to assembling the leg. The assembly is complete. The back drivability looks great. From here, let's move on to motion testing. First, we'll look at position control. In this test, the position control is based only on the actuator's rotor shaft angle. Directly reading the knee joint angle is something I'll leave for another time. As you can see, the position control itself is working correctly. On the other hand, you can also see some vibration at the foot. This vibration is caused by compliance in the transmission mechanism. From this test, it's clear that addressing this compliance will be necessary in the next iteration. The actuator can also achieve faster motions like this. For walking applications, the speed looks more than sufficient. And as shown here, it's possible to drive it even faster. Next, we move on to torque testing. First, 3.4 Newton meters. It lifts the load without any issues. Next, 5.5 Newton meters. This one is also handled stably. Then, 6.9 Newton meters. At this torque level, it still lifts the load reliably. However, at 9.6 Newton meters, there are times when it lifts the load and times when it doesn't. This seems to be around the maximum torque for the current setup. Next, we move on to a durability test. The actuator is operated continuously under a lifting load for 2 hours to check whether any issues occur. 2 hours later, due to compliance in the transmission mechanism, contact has occurred, and as you can see, material has worn away and debris has been generated. This contact likely results in a significant loss of torque. Once again, this indicates that mechanical improvements to eliminate compliance will be necessary. Aside from this issue, no other major problems were observed. So, what did you think? In this video, I built a leg for a quadruped robot. I worked on metal machining using the Carvera Air, and through motion testing, I was also able to identify mechanical issues in the design. In future videos, I hope to show you an improved version of the leg that addresses these issues. If you don't want to miss that, I'd really appreciate it if you like the video and subscribe to the channel. The CAD data for the leg shown in this video is available for download from the GitHub page linked in the description, so feel free to check it out if you're interested. Thanks for watching, and I'll see you in the next video.